For the last lecture class this week, we will talk about the last topic, the engineering design process. After completing this chapter, you will be able to describe engineering design process and the rule graphic plays. You can describe concurrent engineering design process, design for manufacturability, typical members of our design teams. You can explain the role 3D modeling plays in the engineering design process. List and describe the modeling techniques used in the design. Describe the important types for the graphics used to support the engineering design process. Describe the rapid prototyping process. You will describe the ideation process, implementation process, the rules of PDM in drawing control, and lists, and describe the analysis technique used in design. Technical graphic is an integral part of the engineering design process through which engineer and drafter or designer generates new ideas and solve problems. Traditionally, engineering design consists of closely related step documents as paper, graphic, and text that flow in a linear, sequential manner through an organization's. In the face of increased global competitions, many industries in the United States have adopted a team-oriented, concurrent approach using 3D CAD model information as a primary means for communications. In this chapter, describe a modern approach to the engineering design process so that you will have a better understanding of and appreciation for the role of engineering graphic in the design process. Beside the design process, advanced technologies such as product data management, or we call PDM, and web collaborations are also described. Knowledge of how various information management tools and techniques support the evolving design is important to understand the modern design process. For design is the process of conceiving or inventing design and communicating those ideas to others in the form that is understood easily. Most often, the communications tool is graphics. Design is used for two primary purposes: personal expressions and products or process developments, like Figure 1 that I show you in the screen. Artistic design is concerned with personal expressions, and technical design is concerned with product and process development. Technical design has elements of both functional and aesthetic design. Design for personal expressions, usually associated with art, is divided into concrete or realistic and abstract. Design and is often a sort of beauty and interest, like Figure 2. That's one. When a design serves some useful purpose, such as the shapes of a new automobile wheel, it is classified as a design for product or process development, like Figure 3. That one is Figure 3, right? Okay, it's a aesthetic design. Aesthetic design is concerned with the look and feel of a product. Industrial designers specialize in the aesthetic quality of the product as well as other elements related to human-machine functionality. Figure 2 is an abstract design such as the sculpture is meant to evoke a personal emotional response in the viewer, though it does not serve the same functional purpose as the office building behind it. The sculpture enhances the officer worker environment. For Figure 3 is aesthetic design is an important part of the engineering design process. Industrial designers have a major role in the engineering design process for consumer products such as automobile, appliances, and consumer electronics. For Figure 4 is the wind tunnel testing of a new automobile determine how the car would function when moving through the air. This is an example of functional design. And the final figure is Figure 5. For this page, aesthetic and functional design combine to give this sport car a look of speed and elegance. The car is a result of a product design intended to meet the needs of specified markets. Okay, before we move to this page, I will explain you about functional design. Functional design is concerned with the functions of a product and process. Airflow over an automobile is an example of the functional design elements. Most engineers are concerned with functional elements like Figure 4 that I show you on the screen. Many products will have both aesthetic and functional design elements, requiring the engineers and designers to work as a team to produce a product or system that is both functional and aesthetical placings like Figure 5. And product design. For product design is the process used to create new products such as a new automobile model like Figure 5. Okay, Figure 5. A new appliance or a new types of wheelchair. Product design is a complex activity that includes market, production, sales, service, functions, and profit analysis. The goals of product design is to produce a product that meets the wants and needs of the consumer. Is produced economically, is safe for the consumer and the environment, and is profitable to the company. And system design. System design is the process used to create a new system or process. A system engineer or industrial engineer is an engineer who specializes in designing systems. A system is an orderly arrangement of parts that are combined to serve one general functions. For example, an example of a system design includes the arrangement of the assembly process in the factory, like the heating, ventilation, and air conditioning system in the structure, and the electrical system in the automobile, like in Figure 5. The objective is to produce a system that serves specific functions. Economically is safe for the consumer and the environment, and is profitable for the company. Okay, from this page, engineering design is one of the processes normally associated with the entry, business, or enterprise. For research of the order or product design to maintain of the product and all states in between. Figure 6. The design process requires input about such area as customer needs, materials, capitals, energies, time requirements, and human knowledge and skills. Two important societal concerns that an engineer must take into account are legal and environmental issues. Every business must operate within the law that governs their business. When designing, it is important that the engineer understand that legal issues may affect the design products, safety laws related to automobile are an example of how government's legislations can affect a design. Government's regulations related to the environment may also have a bearing on the final outcome of the design. For example, the emissions requirements on an automobile engines have a great effect on the final design. An example of human knowledge input is an engineer knowledge of graphic mathematics and science. Such knowledge is used by the engineer to analyze and solve problems. An engineering design involves both a process and product. Process is a series of continuous action ending in the particular result. A product is anything produced as result of some process. As the design of a product or process is developed, the design teams apply engineering principles, follow budgetary constraints, and takes into account legal and social issues. For example, when a building is designed, engineering principles are used to analyze the structure for loads, determine the structure cost based on the materials to be used, the size of the structure, and aesthetic considerations, and creates a design that adheres to the local laws. Graphic is an extremely important part of the engineering design process. We use graphics as a tool to visualize possible solutions and to document the design for communication purposes. Graphic or geometric modeling using CADs is used to visualize, analyze, document, and produce the products or process. In fact, geometric modeling itself could be considered both a process and product. As a process, geometric modeling produces final design solutions as well as our input to production process in the form of computer database. As a product, geometric modeling is a result of the engineering design process. Form Figure 7 and Figure 8 represent the concurrent approach to engineering design based on 3D modeling. The three intersecting circles represent the concurrent nature of the design approach. For example, in the ideation phase, design engineer interact with our service technicians to ensure that the product will be serviceable easily by the consumer or technicians. This type of interactions result in a better product for the consumer. The three intersecting circles also represent the three activities that are a major part of the concurrent engineering design process: ideations, refinements, and implementations. These three activities are divided further into smaller segments, as shown by the items surrounding the three circles. Design for manufacturability, or we call DFM, and design for assembly, DFA, practice developed out of concurrent engineering as an effort to capture manufacturing and assembly knowledge of formed in the initial design process. This allows engineering and manufacturing professionals to speak a common language that results in the optimized product design. DFM and DFA eventually expand to include other practices such as design for serviceability and design for reliability. This leads to the realizations that it's important to include others in the design process such as marketing, sales, field service, finance, purchasing, and quality control. The center area in Figure 8, that you see from the screen, the 3D computer model, and reflect the central importance of 3D modeling and graphic knowledge in engineering design and productions. Which is used of a modeling approach. Everyone on the teams can have access to the current design through our computer terminal. This data sharing is critically important to the success of the design process through the sharing of information, often in the form of database. It is possible for all areas of the enterprise to work simultaneously on their particular needs as a product is being developed. For example, a preliminary 3D models could be created by the design engineering early in the ideation phase, and the mechanical engineer could use the same 3D model to analyze its thermal property. The information gained from this preliminary analysis then could be given to the design engineers, who then could make any necessary changes early in the ideation phase, minimizing costly change later in the design process. For collaborative engineer has evolved from concurrent engineering into a true enterprise-wide integrated product development process. Concurrent engineering sought to attribute well-defined organizational and team structures, as well as highly structured business process. Collaborative engineering creates the infrastructure and base environments for highly effective team collaborations using computers to store and share information. The development of such tools as email, groupware, video conferencing, and chat rooms were important in the adoption of collaborative engineering in industry. For concurrent engineering is a fundamentally process constrict to the creation of well-defined documents and execute business process for the development of the products. Collaborative engineering is fundamentally a product-centric process that built onto the concurrent engineering practice. A mindset of highly effective collaborations about the product and its manufacturing and support process. The product becomes the central focus instead of the process. Collaborative engineering is based on empower cross-functional team and low-level decisions making. Figure 9 shows the basic structure of the collaborative engineer where cross-functional teams share a common goal through the sharing of information using computer networks. For virtual products representations, collaborative engineer is a highly dependent on computer-based tools used to support the design process include CAD, CAM, CARE, and Office applications. These tools are used to create a virtual representations of a product's design through. One is a shaded CAD model, two is a photorealistic rendering, large assembly visualization, packaging analysis, tolerance analysis, structural, thermal, and flow analysis. 7 is dynamics simulations for design and manufacturing. And finally is virtual realities. Okay, the next one is prototyping. One step closer to realities is gained by using physical prototyping through either rapid prototyping to quickly create a physical model of our parts or functional prototypes to create mock-up of the parts using a traditional means such as machine tools. A rapid prototype is limited. Creating geometric and topological representations of a part. A functional prototype includes geometric and topological representations of the parts in addition to functional representation in terms of mechanical, structural, thermal fluids, and electrical behaviors. The next one is productivity tools. There are a number of tools used to enhance overall productivity and the sharing of design and manufacturing information. These are used by engineers and technicians on a daily basis to support the overall design process, but are not viewed as engineering tools as CAD software is. Tools to share the outputs of the design process include email, word processing, spreadsheets, groupware, file transfer, file translations, video conferencing, and workflow. The next one is EDM and PDM. Tools to manage the long-term overall design or manufacturing process include product data management, or we call PDM, right? And the enterprise data management, EDM. Software programs, EDM and PDM, are used to track and manage all the electronic documents and data associated with the design and manufacturing of the products. Data management always has been important in the manufacturing and design, but is work done traditionally using paper-based filing system. This is being replaced with a digital-based filing system using EDM and PDM software. EDM and PDM software is moving more toward internet browser interface, which especially is important for companies that have operations in multiple locations. The next one is internet, intranet, and extranet. Most of the software tools that describe or used within the context of the computer network to provide the interconnectivity necessary to share information. Recently, the Internet has been the network most capable of providing the interconnectivity for collaborative engineering. Intranets are used as a backbone for internal corporate information sharing. And internal is a private internal network that uses web browser and server to connect users in an organization in order to share information. And extranets are private and secure network that allow access to company internal intranet by outside sources such as supply vendors through the internet. Extranet are the parts of rapidly expanding area of business-to-business information technology that include the internet, extranet, and intranet. The manufacturers of a new product now calls for the involvement of all company departments, engineering, strategy, marketing, and sales, planning, and productions, procurement, finance, and human resource. PLM is a model that facilitates the seamless working of all these departments. It makes it possible to create, manage, simulate, share, and communicate digitally all the information related to the company's products, process, and resource, optimizing its overall performance, like Figure 10. In addition to CAD software used to design, specialized software is required to focus on virtual products management, products data management, and tools for sharing product data across the enterprise. It is possible through the use of computer simulation that problems can be discovered early in the product's definition when changes are laid codely. Companies are using different processes and systems to manage the product data from conceptual design to the field service, and they are looking at ways to improve data flow and streamline processes to increase their competitiveness. A total digital solutions is called PLM. The overall objective is to provide the capabilities for companies to design and simulate products virtually across an integrated enterprise covering the entire life cycle of the product, all without ever having to build a real prototype. This is achieved through advanced in CAD, digital mockup, virtual products modeling, virtual manufacturing simulation, web access, and other key technologies. As a result, companies are dramatically changing the way that they do product design and management, including the integrations of functions within and exploits that to date have been either outside or at the tail end of the product development process. Manufacturers using CAD system produce a tremendous amount of their digital information and knowledge which remain buried in digital form on hard drive and file server. The PLM leverage the knowledge found in this digital file by making that information available to the whole organization. PLM is the integrated information technology environment that allows manufacturers to create, manage, store, and share product data throughout the concept, design, build, and life stage of the product life cycle. It is a business process that plans for the life cycle of the products from proposal to disposal. Although many new technologies have emerged in the 1990s to have had a profound effect on engineering design, the first is web technologies combined with the internet, which made it possible for product data management (PDM) users to access data from remote locations through the web. The second is the realization that geometry and other product information can be reused by virtually all business processes downstream of the design process. Their reusability provides an immense benefits through the elimination of non-value-add activities such as the rekeying of the data, enabling concurrent works as well as avoiding transcriptions and translations errors. So, fundamental has been the impact of these two developments that they have led to profound changes to the way PDM, CAD/CAM, and other computer-aided technologies are developed and used. The increasing use of the same product definitions outside the design office leads not only to tight clubbing of related technologies such as CAD, CAM, and CARE, but also to conversion of these technology with PDM. The internet put an end to any site locations and geographical constraints together. This two development makes it possible for the first time to solve the emerging needs for our business operating in the highly competitive, heavily outsourced global environment. Business can now cut costs and time to market through more effective use and reuse of resources. Be nimble and quick to react to market change through the abilities to focus on core business and increase collaboration with our supplier and partner. Increase our innovations through better visibility of product data to all personnel within both the enterprise and extended enterprise. With a standard web browser as the user interface and encryption technology to provide a secure access across the internet. It's possible for multi-disciplinary teams to work concurrently on the same product data from anywhere around the world. Another significant development is the emergence of the web browser as a standard user interface. This has provided consistency in the presentations of and interactions with product data, making it easy for team members to communicate. And the result is that project teams can include members from a wide range of disciplines as well, including supplier, partner, customers, and other interest parties. These virtual project teams can be set up and disband as the organization's business evolves. And PLM is a strategic business approach for the effective management and use of the corporate intellectual capitals. For corporate intellectual capital, or CIC, is the sum of retained knowledge that an organization accumulates in the course of delivering its products. Corporate intellectual capital consists of the following. One is our product definitions, all the information relating to what the product or service is, its specifications and how it's designed, manufactured, delivered, and support. Number 2 is product history. Any information relating to what the organization has done in the past that is of relevance for delivery of the organization's product, such as all details required for legal or regulatory purposes or actions relating to the past products. 3 is best practice. This summarizes the experience gathered by the organization in the course of delivery of its products. CIC consists of 2 types of data. One is a contents, product definitions, and all related information. 2 is metadata, data that describe the content, such as creations and last modified date, order, owner, version status, how it can be used and by whom, and so forth. PLM allows everyone from manufacturing to marketing and from purchasing to field support to work faster and smarter. This allows the entry network to of the companies working together to conceptualize, design, build, and support product to operate as a single entity. PLM allows companies to share common business processes and a common knowledge of the product throughout all of the stages of its life cycle. From concept to retirement, collaboration breeds innovations and products lifecycle management break down the technologies silo that have limited interaction between the people who design products and the people who build, sell, and use them. Using the collaborative powers of the Internet, PLM increases our company ability to produce innovative product design while reducing cycle times, streamlining manufacturing, and cutting production costs. PLM's stimulus supports and enable three distinct yet deeply interconnected processes. One is supply chain collaborations to help access the product expertise and experience within a company and beyond. Two is product development to help develop better product in a better design environment. And three is enterprise process integrations to help integrate product information with all company business processes. The next one is ideations. Ideations is a constructed approach to thinking for the purpose of the solving a problems. Ideation is that phase of the design process in which the basic design is conceptual phase, feasibility study often are performed to define the problems, identify important factors that limit the scope of the design, evaluate, anticipate difficulty, and consider the consequence of the design. The ideation process consists of three important steps: problems, identifications, preliminary ideas, and preliminary design. Each of these areas can be further subdivided as shown in Figure 11. The ideation process includes problems identification, preliminary idea development, and preliminary design. Ideation is the start of the design process. For refinement, refinement is a repetitive, interactive, or cyclical process used to test the preliminary design, make changes if necessary, and determines if the design meets the goal of the project, like Figure 12. Refinement is the second major stage in the concurrent engineering design process and consists of three main areas: modeling, design analysis, and design visualizations. These areas are subdivided further into activities that ultimately result in the selection of a single design solution. The refinement process includes modeling, design analysis, and visualization. The elements are used to determine if the design meets the goal set earlier in the design process. Refinement is an interactive process which means that changes made to the design may cause elements in the refinement state to be repeated. Modeling is the process of representing abstract idea, words, and form through the orderly use of simplified text and image. Engineers use a model for thinking, visualizing, communicating, predicting, controlling, and training. Models are classified as either descriptive or predictive. For computer simulations, is the precise modeling of complex situations that involve a time element. The 3D computer's model can be used instead of a physical model for property analysis. Material property can be assigned to a computer model so that its behave and look like the real product. For example, instead of the scale model of a new aircraft being made and tested in a war thunder, a computer model can be used to simulate the aircraft in the wind thunder tests like Figure 13. Computer animations is the imprecise modeling of a complex situation that involve our time elements. The major difference between simulations and animation is the degree of precision, and animations only approximately replicate real situations. Simulation accurately replicates real situations. For example, to determine the aerodynamic characteristics of airplanes using a computer simulation, the aircraft and the fluid property software must be represented precisely, or inaccurate information will be obtained. On the other hand, if all that is needed is a visual representation of the aircraft in flight, then the computer model needs to be precise and animations of the vehicle is sufficient. The next one is the design analysis. The design analysis is the evaluation of the proposed design based on the criteria established in the ideation phase. It is the second major area within the refinement process, and the whole design team is involved. Typical analysis performed on the design include the following. First one is a property analysis, which evaluates a design based on its physical properties such as strength, size, volume, center of gravity, weight, and centers of locations, as well as on its thermofluid and mechanical properties. Next one is our mechanism analysis, which determine the motions and loads associated with our mechanical system made of rigid body connected by the joints. Functional analysis, which determine if the design does what is intended to do. In other words, if the design performs the task and meet the requirements specified in the ideation phase. Next one is our human factor analysis, which evaluates our design to determine if the products serve the physical, emotional, quality, mental, and safety needs of the consumer. Aesthetic analysis, which evaluates a design based on its aesthetic quality, market analysis will determine if the design meets the need of the consumer based on the results of the survey or focus groups. The next one is financial analysis, which determines if the price of the proposed design will be in the project price range set during the ideation phase. The next one is I'm talking about is our property analysis. Normally, property analysis is associated with the engineering processes and includes finite element modeling. Property analysis determines if the product is safe and can stand up to the rigor of everyday use. Models are tested under extraordinary conditions, and the information gained can determine if changes might be made to the design. For example, a component might fail under extreme operating conditions. The design team then would recommend changes in the component itself or in the related parts of the product to correct the deficiency, and the model then would be reanalyzed. This interactive process is a major part of the design analysis phase. Finite element model, or FEM, is an analytical tool used in solid mechanics to determine the static and dynamic response of the component under various conditions, such as different temperature, like Figure 14. The fluid mechanics of a design also can be determined using FEM. The interactions of a part with fluid flow, such as water or air, is simulated through the use of color band. For example, Figure 15 shows motions analysis of assembly. The rate of motion is shown using the different color. The FEM proceeds to the 3D computer models as input through a process called discretizations or matching, like Figure 16, and continuous 3D solid model is changed into a model comprised of the multiple polygon shapes such as a rectangle and triangle, which are called elements. Each corner of each element is called a node. After discretizations, the boundary conditions is defined. These conditions describe how an object is typed down. For example, an object bowed down to a surface is called fully constrained. In contrast, an object solo to spin on a shaft is partially constrained. When the boundary condition is defined, property such as material, temperature, and force, and assigned to the model. The model is then evaluated under varying conditions. For example, stress forces are applied fully to constrained model, and the results are shown on screen in the multiple colors like Figure 60. The color represents various levels of stress. The model might also deform to illustrate the effect of the force being applied. The model even could be animated to show the deformations taking place and to show the incremental increase in the level of stress. This process allows the designer to determine if the model will perform safely under extreme operating conditions. The results of the property analysis are used to recommend changes in the design. This analysis is a critical step in the refinement process. Okay, for this page, mechanism analysis, the process concerned with the calculations of motions and loads in mechanical system comprised of a rigid body connected by joints is called mechanism analysis. A camping device is an example of such a system. Mechanism analysis includes assembly, kinematic, and dynamic analysis. Assembly analysis is used to define the individual rigid bodies of the mechanism and to assemble them correctly, considering both geometry and velocity, like Figure 18. When the computer model is used to make the assembly and assign the velocities, the computer uses the engineer input to determine complex geometric and trigonometric relationships. Kinematic analysis determines the motions of assembly without regard to the load. For example, kinematics analysis is used to find the positions of any point on the mechanism at any time during movement of the assembly. To determine clearance and range of motions, computer modeling can be used to trace motion parts in 3D models like Figure 19. Dynamic analysis determines the loads that drive or create the motions of mechanism. This type of analysis can be in the form of the computer simulations, as described in the proceeding section like Figure 20. Thank you everyone for your kind attention.